Hello, my favorite stat students. Hopefully you're ready to start chapter 4. You're feeling pretty good about our first 3 chapters. We really got into some good math in chapter 3 with finding variance and standard deviation, and we'll start working on using those now in problems. So chapter 4 is kind of like its little oasis in the middle of stats. So the class is called Stats and Probability. This is probability, and we use probability, and a lot of it is common sense, but we do have to talk about a few things. So first of all, probability is the chance that an event occurs. We use the word probability. We use the word odds. Odds is a little bit different than probability, so be careful about that. But we're always going to use the word probability and set up problems. And this is really what we use for inferential statistics. So we take an idea from a sample statistic and we apply it to a population. We use that parameter and the probability that something is going to happen. That's really what it comes down to. So a probability experiment is a chance process that leads to outcomes. If you think about it, there might be new terminology, but a lot of this is common sense. So just bear with me. You know how it is at the beginning of a chapter or beginning of a course, there's a lot of terminology and vocabulary we all have to be on the same page with. So an outcome is the result of a single trial. And then we should talk about a trial. So examples of trial, the most basic stuff we do in probability just to get started, flipping a coin one time. How many outcomes are there for flipping a coin one time? There's 2 possible outcomes, right? So we could flip and get heads, we could flip and get tails. A trial might be rolling a die. So a 6-sided die, die is singular, dice is plural. Or, believe it or not, answering a multiple choice question or a true and false question could be a trial. Hopefully you're not guessing. Hopefully you are actually knowing these things. So a sample space, there's 2 ways to show outcomes. The first one is making a sample space. So sample space is the set of all possible outcomes. So tossing a coin is a really short, easy sample space, right? You either get heads or you get tails when you flip a coin. Rolling a die, what are your possible outcomes? You could get a 1, a 2, a 3, a 4, 5, or 6. So there's 6 possible outcomes. That is our sample space. It seems kind of basic when we're just doing one event, but we'll start to add some in there. Answering a true-false question, how many possible outcomes are there? True or false. Tossing 2 coins, so again, we add an extra event. It does matter, say one's a dime and one's a quarter. We're going to flip 2 coins. So we could get heads on both of them. We could get heads on one and tails on the other. We could get tails and heads. Those are 2 different things. If you think about it like one's a quarter and one's a dime, it depends which one you've got. And we have one more outcome, right? We could get both tails. So that's our sample space for tossing 2 coins. We could actually do an experiment and see which one of those outcomes we end up with. So choosing a card from a deck. I put this in your notes so that you could actually have a deck of cards. Some people don't know cards anymore, which is always amazing. I know that it doesn't come out really nice if you've got a paper copy, but hearts and diamonds are reds. And aces. Clubs and spades are black cards. So I could say, how many possible outcomes if you draw 1 card from the deck? Well, if I've got 4 suits and there's 13 cards in each one, there'd be 52 possible outcomes. I listed all of them for you. So this is a sample space. This sample space might come in handy as we do problems this chapter. So keep that at hand if you need to double check that. All right. So 52 possible outcomes. All right, sample space for rolling 2 die. So this one I didn't make for you. So I should have said rolling 2 dice. So if I'm going to roll 2 dice, how many possible outcomes are there? Well, let's say I've got 2 dice. One of them is green, and one of them is purple. I just want to make sure I clarify that some things it makes a difference, just like I said, if we flipped a quarter and a dime. So if the quarter's a head or if the quarter's a tail. So I just want to make sure I clarify that. So really, here's our possible outcomes for each die. This is possible outcomes for green. And this is the possible outcomes for the purple die. But now when we're rolling 2, we know that if you roll 1 die, there's 6 possible outcomes, right? Well, if we roll 2 die, we've got combinations of things. So we could get a 1 and a 1. We could roll and get a 1 and a 2. We could get a 1 on the purple and a 3 on the green. A 1 on the purple and a 4 on the green. We could get a 2 on the purple and a 1 on the green. 2, 1 and 1, 2 are 2 different possible outcomes, especially if you keep in mind you've got 2 different colored die. So I'm going to hit pause right here and I'm going to fill in my sample space. You go ahead and make sure you have your sample space filled in because we are going to use this sample space as well as the card one quite frequently. Hopefully your sample space looks something like that. So how many possible outcomes are there? How many different possible combinations of dice, of rolls could we get for that green die and purple die? Looks to me like there's 36 possible outcomes for 2 die. So again, remember, 2, 1 and 1, 2 are 2 different things. That S is not what it's supposed to be right there. All right. So there's our sample space, 36 possible outcomes. Keep that in mind. We're going to refer back to this as well. All right, so we could make a sample space. The other way to show all of our possible outcomes is a tree diagram. So we're going to just use a tree format instead of a list or instead of a table. So if I'm going to have 3 kids in my family, in a family of 3 children, find the sample space as a tree diagram for the birth order by gender of the children. So the first child, the second child, and the third child, right? So let's say child 1. We've got 2 options, right? Our first child could be a boy or a girl. So underneath child 1, I'm going to say a boy or a girl. Leave a little space. Then I have to take into account, now we're going to have a second kid. And then we're going to have a third child. We're stopping after that. So my second child, if the first child is a boy, what are my options? What could I have for my second child? Does it matter what the first kid is? Doesn't really matter, right? The second child could be a boy or a girl. If my first child's a girl, I could have a boy or a girl. And then for my third child, if my first one's a boy, my second one's a boy, my third one could be a boy or a girl. If my first one's a boy, second one's a girl, this one could be a boy or a girl. You see why you need to leave a little space. If my first one's a girl, second one's a boy, this one could be a boy or a girl. And if I've got a girl and then a girl, I could have a boy or a girl for my third child. So if I count down, you've got 2 ways to kind of look at how many possible outcomes there are. I could read across every one. I could say boy, boy, boy is one possible outcome. Boy, boy, girl is a second possible outcome. Boy, girl, boy is another possible outcome. So when you read across that tree and take different branches, you've got all of your possible outcomes for the birth order by gender of children. If you just want to count how many possible outcomes there are, your last part of your tree will be how many branches there are. So it looks to me like there's going to be 8 possible outcomes for birth order for 3 kids. So there's a tree diagram. So there's 2 ways to show our possible outcomes. You could make a sample space or you could make a tree diagram. Most people prefer a sample space. A lot of people like the tree diagram though because it really shows and you can kind of make sense of it. I put the little headers at the top of each one so that I know what I'm talking about. The first child, the second child, the third child. All right, so let's talk about events. So an event is the set of outcomes of an experiment. A simple event is just one outcome. I flip a coin and I get tails. So instead of listing all the possible outcomes, it is the outcome. I look at a family with 3 kids and I look at, well, that's not a simple event. Compound event has more than one outcome. You flip a coin and you roll a die. So you do your probability experiment, you look at what your possible outcomes are, and then the event is the actual outcome itself. So there are 3 types of probability. So bear with me. Classical probability is also known as, I usually call it theoretical, if I can spell it. Theoretical probability is, in theory, what should happen, right? This is, if the world were perfect, which it's not, what would potentially happen? So we use our sample spaces. So we write down all of our possible outcomes for rolling 2 die, and then we just base everything off of those sample spaces. Remember, there's 2 ways to make sample spaces, a tree diagram or just a table. Whoops. The probability of any event A, so it's just saying of A happening, maybe we want A to be getting tails when we flip a coin. So the probability of any event A is favorable over possible. They say K over N. I never remember K over N. I always say favorable over possible. You could start a game, and every time I say favorable over possible in this chapter, let's count it up and see where we're at. I missed this bullet right here. This assumes, remember, it's theoretical. So we assume that all outcomes are equally likely to occur. There's no rigged dice, there's nobody counting cards, there's nothing happening. Every outcome is equally likely. So favorable over possible is our huge, very important formula that we're going to use for the whole rest of the chapter. And last but not least, you can write your answers 3 ways: fractions, decimals, or percentages. If you're doing a decimal, round to the nearest thousandth. That would be 3 numbers after the decimal. So if you're doing a percentage, that means you're going to have like an 89.1%. Fractions, obviously, you don't round. Some things lend themselves to fractions because the numbers are really messy or your calculator doesn't like it. So we'll kind of talk about that. If you're ever in doubt, ask me how you should write your answer. All right. So let's do just a basic find the probability. So we filled out that sample space for the gender of 3 children, right? So what's the probability that all 3 of the children are of the same gender? So probability of same gender, that's our event A, equals favorable over possible. So how many possible outcomes did we say we had? Look back at that tree diagram we made. Weren't there 8 possible outcomes? We could go through the list of all of them. And then same gender. So in other words, we want them all to be boy, 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 or girl, 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 right? It doesn't matter. We're just saying same gender. So how many possible outcomes were there that had the same gender in them? I believe there was just one list that had all 3 boys and one list that had all 3 girls. So 2 out of 8, which of course we're going to simplify down to 1/4. So there's a 1/4 or 25% probability that a family of 3 will have all the same gender, all 3 boys or all 3 girls. So if you want to write it as a 0.25 or at 25%. 1/4 seems really easy to just leave it. I brought down that table about finding the sample space, but we already did that, so we are good. All right. Hopefully everybody finds that easy, favorable over possible. If you're ever stuck, think, okay, well, how many possible outcomes are there, and then what am I looking for? So there's some rules for probability. First rule is probability is always between 0 and 1. So I got all fancy here, and I said 0 is less than or equal to the probability of A, which is less than or equal to 1. Probability of A, remember, is any event. It doesn't matter what we're talking about. The probability is always between 0 and 1. If you like percentages, the probability is always between 0% to 100%. There is no 150% probability, 0 to 1. So I put that little number line on here, right? So 0 is impossible. If there's a 0% probability, it's not going to happen. If it is a 100% or the probability is equal to 1, it is absolutely positively going to happen. What's the probability that this lesson is going to be longer than you want it to be? Probably 100%, right? I'm not even offended. Second characteristic, the sum of the probabilities of all the outcomes has to be equal to 1. We'll use that when we go through. So basically our whole sample space equals 1. So all of the possible outcomes add up to 1. We know this already, mentioned it. If an event cannot occur, the probability is an absolute 0. And on the other end of that, if an event is certain, your probability of any event, is equal to 1. So those are the 4 big rules. I'm actually going to ask you about a couple of those on worksheet, and just so that you understand what probability really looks like. All right, let's talk about a couple quick things here, and then we'll go on to empirical probability. So consider rolling 1 fair die. Find the probability of rolling a 5. So probability of any event is favorable, what you're looking for, over possible. This first question seems super easy, right? So we'd write it this way. The probability of a 5 is equal to, well, how many possible outcomes are there? That's always my denominator. How many 5s do you have on a die? 1, right? So a probability of a 5 is 1 out of 6. Probability of a multiple of 3. So the multiples are 3, 6, 9, 12. Only 3 and 6 would be relevant if we're talking about rolling a die. So the probability of a 3 or a 6 is equal to, we know we have 6 possible outcomes. How many 3s or 6s do we have on a die? 1 of each, right? So 2 out of 6, or 1/3. The probability of rolling an 8, everybody knows that's a big old 0, right? 0 out of 6. Practice 6, find the probability of rolling a value less than 7. So probability less than 7 would be anything 1 to 6 if we roll a die. What's the probability of that? We have 6 numbers that are less than 7 out of 6 possible outcomes. So 100% probability that we roll a die, we're going to get 1, 2, 3, 4, 5, or 6. All right, complementary events. These ones are interesting because they give us another way to figure things out. So complementary events, we do favorable over possible, right? Complementary is unfavorable, what we're not looking for. So what's the complement of rolling a die and getting an even? The complement would be getting an odd. The complement is an odd number. So what we're not looking for. We call that A bar. So the probability of event A is what we're looking for. Probability of A bar is the complementary event, the opposite or the other side of it, or the unfavorable. So the probability of A bar is 1 minus the probability of whatever we're looking for. That's the most crucial one. Feel free to write down the other two if you want, but that one makes the most sense. The other's just algebra. Really, it comes down to, it starts with this. Remember how we said the sum of probabilities always add up to 1? Well, the probability of A plus the probability of A bar is equal to 1. What we're looking for and what we're not looking for is equal to 1. So if I ask you in practice 7 to find the complement of event A, I want to select a day. I'm going to put all the names of, or all the days of the week in a hat and select a day that begins with a T. So Tuesday or Thursday. What is the complement of that? So A bar would be equal to any day that does not start with a T. So like probably, what? Saturday, Sunday, Monday, Wednesday, Friday. So that would be our A bar. Make sense to everybody? Are we all good there? So, and then if I asked you for the probability of that, we'd say, well, so the probability of A bar would be equal to unfavorable over possible, or we're looking for 5 different days out of 7 possible days. Probability of A, Tuesday or Thursday, would be 2 out of 7. Notice 2 sevenths plus 5 sevenths adds up to 1 whole because we've accounted for every single day in the week. We'll keep working on those complements. Those ones are interesting, and like I said, sometimes it helps us to do a problem in an easier way. Empirical probability. We're moving on to the next one. I usually call this one experimental. So classical was theoretical, right? In theory, what should happen? Empirical is an experiment. We're actually going to do some kind of probability experiment. So it relies on actual experience. And notice, I threw in an old term from chapter 2, I think it is. We're actually going to be finding relative frequencies. So that's how this probability and stats all ties together. You perform the experiment, or you get data and use it. And hopefully at this point, you know that probability, you've heard me say it so many times already, is favorable over possible. Well, in this case, we're going to say the frequency, the number of times we got that outcome, over n, the total number of experiments or trials that we did. So frequency over n, it's exactly what we did in our frequency table when we found relative frequencies. We're actually finding empirical probability. And last but not least, we're going to use this the same as relative frequencies. I'm typically going to tell you to leave this as a proportion or a decimal if you prefer. 3 decimal places. All right. So, quick example, empirical probability of blood type. So I'm not doing an experiment, but I am collecting the data and using it. So we had a survey of a blood type of 50 people. 21 have type O, 22 have type A, 5 have type B, and 2 have type AB. Find the empirical probabilities. So empirical probability is equal to frequency over n. So the probability, you notice the notation, P stands for probability. Probability that a person has type O blood would be 21 people, right? Out of our N, our sample size, 50. We could leave it that way as 21 over 50. We could go to a decimal, which would be, what, a 0.42. Or if you liked, we could say that was 42%. I'm typically going to leave it as a fraction or go to the decimal. So type A or AB blood. So A is 22. Whoa. AB is 2. So if I have either of those, that looks like a 24 for our frequency over 50 for our sample size. So, whoa, that's going to be like a 0.48. Or a 48%. Easy peasy, right? Notice the last one, a person has neither type A nor AB blood, so the complement of the problem we just did. So if 48% of the people have A or AB blood, we could say that's like 1 minus that 0.48, or we could add up the other two and see that it's 26. That ends up being a 0.52, a 52%. So it's really a different way to do it. Sometimes you don't have to use that, rely on that complement. Other times it's helpful. The law of large numbers has to be talked about when we talk about empirical probability, because this is used and it says this: as your n increases, your relative frequency becomes closer to theoretical. Remember, it's not a perfect world. When we actually do an experiment and re-roll a die 6 times, theoretical probability tells us that we should get each number 1 time. However, experimental probability isn't going to work that way. You could get 6 on every roll because you're doing an actual experiment. But if you roll 6 times, you're going to get maybe off-balance results. But if you roll 600 times, it's going to start looking more and more like theoretical probability. So if you toss a fair die, your theoretical probability for rolling a 2 is favorable over possible, right? So there's 1 2 out of 6 possible outcomes. So, but in the experiment, as the number of tosses that result in 2 increases, empirical probability will approach 1 out of 6. If you just flip it 1 time, you may or may not get a 2. If you flip it 6 times, you should get a 2 once, but you might not. So the more you go, the more trials you go, the more close you will end up being to theoretical probability. All right, last but not least, I promise this is it. The last kind of probability. So we've got classical, which is theoretical. We've got empirical, which is doing an experiment. And then we've got subjective. If you know the word subjective, that means that it can be influenced or it's not based on necessarily exact science. Subjective is based on educated guesses, opinions. So, you know, if we're in the middle of a presidential election, a lot of people are making educated guesses. That's subjective probability. They probably have some data that leads them to believe things, but you just don't know. So this is based on experience, evaluations, data, but it's a prediction into the future typically. So I've got a couple examples like weather forecasting, right? We have all kinds of Doppler models out there, but we still can't be exact. We don't know exactly that rain is going to come at 8:45 a.m. Or a lot of sports predictions, like who's going to win the Super Bowl. The Lions are going to win the Super Bowl this year. It's all predictions. It's subjective. Or I'm going to add this one on there because it seems like we should. I'm going to say outcomes of an election. It's subjective. We don't know. We are making our best educated guess that we possibly can. So 3 types of probability. Subjective, that's all we're going to talk about it. You just need to know that it's there. The other 2 we're going to do a lot with. And don't forget, favorable over possible is how you find probability. That is the end of section 4.1. Thanks for hanging in there, guys. See you next time.